Okay, now we're going to take a look at question number 21. So this is kind of starts the content from chapter 8 of Chemistry 111, and this is practice exam 4. Question 21, which of the following elements is found as a diatomic species in its most stable form? I'll ask my students, can anybody come up with an answer for this one? Which one of these is a diatomic element? Which one exists as a diatomic element? A packet of 2. Yeah, thanks, Christian. Absolutely. It's bromine. There are many different acronyms going out around there. I like the one which is have no fear of ice cold beer. And so, as Kristen said, the answer is bromine. Bromine exists as a diatomic species. You see, there's a couple other tricky ones in here, right? Sulfur can come in a packet of 8, and phosphorus comes in packets of 4, but that's not diatomic. That's tetratomic and octatomic. So we have diatomic as being bromine. You need to be fully aware of all the diatomic elements. Question 22. Which of the following is the general electron configuration for the outermost electrons of elements in group 5A? So you need to know that group 5A is, if we go from group 1A to 2A, then boron starts 3A, carbon is 4A, and where nitrogen is, that is group 5A. So if you look at nitrogen, phosphorus, arsenic, antimony, bismuth, what should their outer electron configuration be? Well, let's take a look at nitrogen, for example. So we'll say, for example, nitrogen. The noble gas that precedes nitrogen is helium. And after that, we have 2s2, 2p3. So it means we're going to have ns2, np3, right? Both of the n's are the same. And so the answer is B, ns2, np3. So if you go nitrogen, phosphorus, and keep going down the group, all of them will end with ns2, n3p, or have those for their outermost electrons. Question number 23, consider the element with the electron configuration krypton, 4s2, 4d7. So krypton is element number 36. It says this element is, well, if it ends at 4d7, right, if it ends in the D block, so ends in D block, this must be a transition metal. Transition metal. All right, so there we go. This is a transition metal. Question number 24. Which of the following is the general electron configuration for the outermost electrons of the halogens? Halogens being helium, neon, argon, krypton, xenon, and radon. You can't just use helium for this one because helium only has s electrons available to it, but there's no answer that fits helium anyway. If you look at neon, for example, again, we're just using neon as an example. We have neon, we have helium, and then after helium, we have 2s2, 2p6. And so it would be ns2, np6, and that is this answer right. Shit, did I say halogens when I meant no? I was talking about noble gases. Nobody stopped me. Jeepers. Okay, so I'm talking with the halogen. So instead of neon, I'll pick fluorine. There we go. So if I have fluorine, it's 2s2, 2p5. There we go. So I'll fix that. So ns2, np5 is the correct answer. There we go. Sorry. I read halogens and I had noble gases on the brain, I guess. Okay, number 25. How many valence electrons does sulfide have, right? This is polyatomic ion. This is sulfide. Well, if we look at the electron configuration for sulfur, which is element number 16, the noble gas that precedes sulfur is neon. And then after neon, we have 3s2, then we have 3p4. That's for sulfur. But if I have S2 minus, since I have 2 minus, means 2 more electrons. So I'd add the 2 electrons to the p orbital because there's room for 2 more in there. So that means that sulfide is going to be neon 3s2 3p6, which makes sense because now it's isoelectronic with a noble gas. It's isoelectronic with argon. But how many total electrons do we have? Well, neon itself has 10 electrons. I have 10 plus 2 electrons plus 6 electrons. I tally all that up, and that gives me a total of 18 electrons total, but it's asking us for the valence electrons only. The valence electrons are the outermost electrons, and so my valence electrons are the ones with the highest principal quantum number, being 3, and so the answer is 8. So 3s2, 3p6, I take 2 electrons plus 6 electrons, and I get 8 electrons for my valence electrons. Next question, 26. How many electrons are in the 4p subshell of vanadium? Vanadium is element number 23. So there's vanadium. And we want to find out how many electrons are in the 4p subshell of vanadium. Well, let's write out the electron configuration of vanadium. The noble gas that precedes vanadium is argon. And after argon, we're in the 4th period, so we have 4s2. Vanadium is the 3rd transition metal in, so we have 3d3. Therefore, there are no electrons in the 4p subshell. And so the answer is 0. I have no 4p electrons. Question number 27, concerning the electron configuration of sulfur, which we already looked at this evening. Which of the following represents the core electrons only? Well, core electrons are another way of saying non-valence electrons. Non-valence electrons. If I go back to my electron configuration here, my valence electrons are the ones with the highest principal quantum number. These ones here. These are valence electrons, which means that anything that precedes that, the 1s2, 2s2, 2p6, these are my core electrons. So I go over here and I look for that answer, which is C, 1s2, 2s2, 2p6. So you need to know the difference between valence electrons and core electrons. Number 28, which of the following elements forms a stable 3- anion? The 3- anion, if it's a stable 3- anion, it must be isoelectronic with a noble gas, right, to form that stable anion. Well, if I look at group 1, 2, 3, 4, 5a, an element like nitrogen, for example. So if you look at 5a elements, and we looked at their generic electron configuration this evening for their valence electrons, if I'm a 5a element, I have an electron configuration which ends in ns2, np3. So if it gains 3 electrons, it's going to have a noble gas configuration. It's going to have ns2, np6, which again would be isoelectronic with a noble gas. So all I have to do is look for an element that is in group 5a. My 5a elements are nitrogen, phosphorus, arsenic, antimony, and bismuth. And so the answer is phosphorus, which is in group 5a. Question number 29. Which of the following elements forms a stable 2+ cation? I think that we went over this enough in class that you should know that this element is going to come from group 2a. It's going to be an alkaline earth. Alkaline earths, when they lose 2 electrons, they become isoelectronic with a noble gas. What are the elements that are alkaline earths? We have beryllium, magnesium, calcium, strontium, barium, and radium. And so the answer is barium, because barium 2+ is isoelectronic with xenon, which is a noble gas. Question number 30 asks us which one of these is not isoelectronic with the others. Well, let's take a look. Bromide, Br minus, we take bromine, we add 1 electron. That is isoelectronic with krypton. The next one is rubidium with a +1 charge. Rubidium is element number 37. If it loses 1 electron, it is also isoelectronic with krypton. The next one is selenium with a 2- charge. Selenium is element number 34. It's right next to bromine. If it gains 2 electrons, it becomes isoelectronic with krypton. The next one is strontium with a 2+ charge. If you look at strontium, it's element number 38. If it loses 2 electrons, it will have 36 electrons, and it will become isoelectronic with krypton. However, tellurium with a 2- charge, if I look at tellurium, it's element number 52. It's isoelectronic with xenon. And so the answer is tellurium 2- is the outlier. It's isoelectronic with xenon. Question number 31, which of the following is the electron configuration for the aluminum ion? Well, you need to know, and I went over this with you in class when we discussed oxidation numbers, that an aluminum ion is always aluminum 3+. If I write out just the electron configuration for aluminum itself, we could do the whole thing 1s2, 2s2, 2p6, 3s2, 3p1. Well, if it's 3+, that means it has to lose, or I could say here, lost 3 valence electrons. So these electrons are going to be lost when I form Al3+, and I'm going to end up with 1s2, 2s2, 2p6. And so the answer is C, 1s2, 2s2, 2p6. Number 32, which of the elements below has the highest first ionization energy? Well, if we're looking at the periodic table, and this is just a generic sketch, I guess I could make it a little bit better. A generic sketch of the periodic table, maybe something like this, I don't know, something like that, roughly. We know that ionization energy increases as we go across a period, and the ionization energy increases as we go up a group. And so we're looking for something that's in the top left of the periodic table. I have all these elements, oxygen, selenium, which are both in the same group, carbon. I also have germanium, and what else do I have? I have phosphorus. So they actually form kind of an X on the periodic table. They actually form something that looks like this, and this, I guess. So I have my oxygen up here. I have carbon over here. I have phosphorus right here, germanium over here, and down at the bottom I have selenium. Okay, could anybody tell me which one of these would have the highest first ionization energy? And it's not a trick question. Yeah, thanks, Anthony. Absolutely. It's the one that's highest and to the right. So ionization energy increases up and to the right. And remember that ionization energy is the amount of energy required to remove an electron from an element in the gaseous phase. Let's move on from there and talk a little bit more about electron configuration. Which of the following does not have krypton as its electron configuration? Well, we know that krypton is element number 36. So we're looking for things that have 36 electrons. If you look at selenium with a 2- charge, selenium is element number 34. So if it gains 2 electrons, it's going to have 36 electrons. So that means it's isoelectronic with krypton. The next one is ytterbium with a 3+ charge. Ytterbium is element number 39. If you take 39 and you subtract 3, what do you get? You get 36 electrons. The next one is bromide. Bromine is element number 35. If it gains 1 electron from one negative charge, it has 36 electrons. If we look at rubidium with a +1 charge, rubidium is element number 37. If it loses 1 electron, it will have 36 electrons. However, if I have zinc with a 2+ charge, zinc is element number 30. Remember that zinc has an electron configuration of, or outer electron configuration of 4s2 3d10. So it would just be 3d10 because it would lose the 4s electrons first. But either way, it is not going to be isoelectronic with krypton, not even close. Because zinc has 30 electrons, so when it loses 2 electrons, son of a gun, why does it keep doing that? It's going to have a total of 28 electrons. So we'll put here 28 electrons like that. And that might be an easier way to think about it. Okay, number 34. What is the effective nuclear charge felt by the outermost electrons? With the effective nuclear charge, ZF, felt by the outermost electrons is strongest for which of the following elements? We make a little periodic table here. There we go. We know that effective nuclear charge increases when we go across a period. We know that effective nuclear charge also increases going down a group. However, because of the size of the elements as they get bigger and bigger as you go down a group, the ionization energy decreases. But anyhow, generally speaking, we know that ZF increases going up and to the right like this. And so if I look at all of these elements, I have carbon, nitrogen, and oxygen, and boron, and they all come next to each other like this, as does fluorine. So we have boron, carbon, nitrogen, oxygen, and fluorine. Well, I think it's pretty obvious that the one that's going to have the highest effective nuclear charge is going to be fluorine, because as we go across the period, effective nuclear charge is equal to the number of electrons or protons subtract the number of core electrons. And so as we go across a period, we have more and more protons in the nucleus. However, the number of shielding electrons doesn't change, does it? And so the effective nuclear charge increases as we go across a period. Question number 35, which one of the following ions has the largest radius? I'll just throw this out there to my students. Does anybody have an answer for this one? Let's take a look at how many electrons each one of these has. Thanks, Anthony. I think you're definitely on the right track, right? Let's take a look. If we have a potassium ion, it's going to have 18 electrons. If I have an oxide, O2-, it's going to have a total of 10 electrons. If I have a sodium cation, it's got a total of 10 electrons. If I have a chloride ion, it's got 18 electrons. But if I have a sulfide, it's also got 18 electrons. We can immediately remove the two that have only 10 electrons, right? Because we know their principal quantum number is not going to be as high. But if we look at A, D, and E, they all are isoelectronic with one another. They all have the same number of electrons. But what do we know? We know that sulfur, out of all of these, has the lowest atomic number. That means it's got the lowest number of protons, so least number of protons. And if it has the least number of protons in the nucleus, that means it's got the less amount of positive charge trying to rein in those 18 electrons. So if it has the least amount of positive charge trying to pull in those electrons, that means they're going to be further away from the nucleus. And so the sulfide is going to have the largest radius. We could also add on top of that and say we're adding more electrons to the highest subshell. And so they're going to start to repel each other, and they're going to need more space. And that is why sulfide is going to have the largest radius of all of these ions. Number 36 says arrange the following ions in order of decreasing ionic radius. So we want to go from large to small, right? We want to go from large all the way down to small in order of decreasing, right? Well, which one of these is going to be the biggest? Well, the first thing I want to do is figure out how many electrons each one of these have. If I look at aluminum, aluminum is element number 13. If I have aluminum 3+, it's going to have 10 electrons. Magnesium is element number 12. If it's magnesium 2+, it's going to have 10 electrons. Look at this. Sodium is element number 11. Sodium plus is going to have 10 electrons. And you can probably see where I'm going with this. Oxide is element number 8. I add 2 electrons. I've got 10 electrons. Well, how many protons does aluminum have? Right? Aluminum is element number 13. It's got 13 protons. Magnesium has 12 protons. Sodium has 11 protons. And oxygen has 8 protons. Well, hopefully you can see which one of these is going to be the biggest, right? Whichever one has the least number of protons to try to rein in those 10 electrons, same rationale that we applied in the last question, oxide is going to be the biggest of all. Could anybody tell me which one of these would be the smallest? And it's not a trick. Thanks, Branson. Yeah, it's going to be the aluminum cation, isn't it? The aluminum 3+ ion is going to be the smallest. Why? Let's think about it. We have 13 positive charges in the nucleus. We have the most of all the positive charges in the nucleus trying to rein in the same amount of electrons. It's going to suck them in way more than any of the other ions. And so our aluminum 3+ is going to be the smallest. And using the exact same rationale, we have our sodium is going to be the second largest, and then magnesium 2+ is going to come next, and then we have aluminum being the smallest. And so the answer is B, right there. Question number 37. For which of the following reactions is the enthalpy change equal to the third ionization energy of vanadium? Well, if we're dealing with the third ionization energy of vanadium, we are going to have removed 3 electrons from vanadium. Let me walk you through this. We have vanadium in the gaseous phase. And as we talked about in our last lecture, we have an ionization energy, we'll call it ionization energy 1, associated with the removal of an electron from the vanadium to form a vanadium cation plus an electron. That's the first ionization energy. This is the first one. The second one, the second ionization energy, is where we start with that vanadium cation. We apply a second amount of energy, we'll call it I2, and we form a vanadium 2+ cation in the gaseous phase, and we also release an electron. And so the answer is going to be the third ionization energy, means we need to put even more energy in to our vanadium 2+ cation in the gaseous phase to form a vanadium 3+ cation in the gaseous phase and release another electron. And so the answer is the vanadium 2+, which produces the vanadium 3+ plus an electron. The I just represents the amount of energy that goes into it. So this actually represents the reaction that shows the enthalpy change for the third ionization energy of vanadium. You can see the problem with A is that you're starting with an anion. You can see the problem with B is that this is the fourth ionization energy, right? Because we're removing the fourth electron to form a 4+ cation, so that's not right. The next one, I don't even know what the hell is going on here, because ionization energies are only the removal of 1 electron, not 3. And then here, this is a reduction, right? We're adding electrons, and ionization energy is associated with removing electrons, not adding electrons. Question number 38 also deals with ionization energies. The successive ionization energies for an element are I1 is equal to 589.5 kilojoules per mole. I2 is equal to 1145 kilojoules per mole. I3 is equal to 4900 kilojoules per mole. I4 is equal to 6500 kilojoules per mole. And I5 is equal to, 8100 kilojoules per mole. This pattern of ionization energies suggests that the element is, could anybody tell me how many valence electrons this element has based off of these ionization energies? Yeah, thanks, Branson. It's 2, because we see the biggest change in ionization energy, or the biggest energy gap, right here. Oops, I have to use a blue pen. So we'll say from I2 to I3 has largest delta E, or largest delta I is what I should say, really. Change in ionization energy. And so that tells us that the first 2 electrons, these 2 electrons are valence electrons being removed. And all of these, since they cost way more energy, these are core electrons being removed. So that means I'm looking for an element that has 2 valence electrons. It's not potassium, it's calcium, because calcium is in group 2A. So it's got 2 valence electrons. There you go. It's definitely not sulfur. It's not arsenic. And it's not silicon. Those are way over in the P block. They definitely have more than 2 valence electrons. Let's see here. Number 39. What are the products of the following reaction? Well, this is a redox reaction that's occurring here. So what we're doing is we're taking the aluminum and we're combining it with acid, 6H plus like this. And this is one of those sections that I asked you to read from the textbook because we didn't have time to cover it in a lecture. And so it goes over this reaction. We're basically combining a metal. So this is a metal plus an acid. And what we end up generating in this case is we end up oxidizing the metal and producing hydrogen gas. So if we're going to produce hydrogen gas, we can just write H2 gaseous like this. And if we're oxidizing the metal, well, what's aluminum going to be oxidized to? It's going to be oxidized to an aluminum 3+ ion like that in the aqueous phase, since I'm doing the reaction in aqueous acid like this. So now I just need to balance it. So I need a 3 over here, and I need a 2 over here like this. And so the products are 2 aluminum ions and 3 moles of the gas, of hydrogen gas. And again, this section, I can't remember exactly which section it is, but it's the part where it talks about group 1A elements, group 2A elements, group 3A, and then it covers this reaction. And the last one is something that I did mention to you very quickly when we were running out of time in our last lecture, which is where I talked about oxides. If you look at the periodic table, okay, and you form an oxide of elements that come from the left-hand side of the periodic table, they form basic oxides. From the right-hand side, we form acidic oxides. And then somewhere in the middle, we form what are called amphoteric oxides. So they can be, acidic or basic depending on the situation. And so we're looking for an oxide that is combined with a metal from the left-hand side of the periodic table. We're looking for something that's over here, something that's a metal. Well, the only one that fits the bill is magnesium. It's in group 2A. Chlorine, right? Chlorine is in the P block. Carbon is in the P block. Arsenic is in the P block. And sulfur is in the P block. This one is in the S block. So it is the only one that's going to form a basic oxide.